Hi, everyone. Thanks for this chance to introduce our project and tool to you today. I'm Andrew Kong from UC San Diego, and Tom Spyru has been at UCSD since this past July as the Chief Architect and Technical Project Manager of OpenRoad. Tom is one of the industry veterans who's been helping to bring OpenRoad from academic research to an EDA tool. After this intro, Tom will walk you through our project and show a demo. We're glad to also welcome Mohammed Shalan, who will tell you about eFabulous' experiences with OpenLane and the OpenRoad tool. And we look forward to the Q&A session on Sunday. OpenRoad tackles a crisis which has been decades in the making. Everyone's here today really because design is just too difficult. A modern place and route tool has a huge number of command option combinations. The tools have become complex as they handle increasing design rule complexity, so outcomes are harder to predict and expert users are needed. This brings cost and risk that are not good for anyone. And we see pictures like this. The cost of silicon stays at a nickel or a dime per square millimeter, but the cost of designing that square millimeter is out of control. So one path forward is to automation with self-driving design tools and flows. OpenRoad is a project in the DARPA IDEA program, which aims for hardware compilers 2.0, no humans, 24-hour turnaround, eventually with zero loss of quality. This shifts the focus from tools that eke out that last picosecond of clock period to self-driving tools that don't require expertise or time to tape out a working chip. The broad impact is to restore designer access to silicon. Our project is tasked with achieving the Silicon Compiler's 2.0 vision for the digital IC RTL to GDS flow, Verilog in, and merged GDS tape-out database out. This is our website. You'll see that we aim for automated 24-hour digital design while also catalyzing an open source ecosystem for researchers, tool developers, and users. Our team has 4 universities plus Qualcomm and ARM. To get from design complexity to 24 hours and no humans, several key technologies are required. First, partitioning to decompose the design problem into bite-sized chunks, orchestration of distributed and parallel optimization threads, and machine learning to model and predict what happens when a heuristic is run in some way on some input with some target. And there's freedoms from choice, which we expect in a no humans tool, just as self-driving cars might eventually have no steering wheel. This is research. And we have some key mindsets behind the project. Our RTL to GDS flow runs from logic synthesis through detailed routing and then layout generation. It takes all industry standard formats for timing and power libraries and so on, plus some additional config files and characterizations. Output is final routing and GDS out, plus timing and power reports. Last July, we showed an alpha milestone of DRC clean RTL to GDS in TSMC 65LP with ARM cells and IPs. Today, we're a couple of months from our V1.0 release, and some more information is available at these links. Just 2 of many possible shout-outs. James Cherry's OpenSTA timer has been a huge breakthrough for EDA open source. It's a commercial timer that's been embedded in about 15 commercial EDA tools, including most FPGA tools. And this slide shows Slack histograms, WNS, TNS from a commercial sign-off timer and from OpenSTA on a small 28 nanometer block. The differences are on the order of a few tens of picoseconds. And as you'll see in a later slide, the incremental STA engine, keep an eye out for it, is totally central to a modern RTL to GDS tool. Another shout out, Replace was open sourced at the start of our project, and it's used for global placement. It's also under the hood of our IO placement and macro placement engines. Before Tom starts the demo and walkthrough, we made a few slides to preview some key takeaways. This slide shows one takeaway. It's about tool architecture and software quality, which Tom will talk about, and give some main links. OpenRoad has the architecture of a modern EDA place and route tool, which is shown here. And here are some links that Tom will explore with you: the project, the flow, the top-level application. Here's what you'll see next. And here's what you won't be seeing due to time constraints, but you can replicate this at home. With that, thank you for your interest in OpenRoad, and I'll turn things over to Tom.
Hi, my name is Tom Spiro. I'm the Chief Architect and Technical Program Manager of the OpenRoad project. And I'm here today to discuss with you a little bit about the OpenRoad project, what the goals are, and then to move into a live demo. So to start off with, the OpenRoad project is focused on democratizing hardware design, which is doing so through building a new EDA tool suite, which is focused on full automation as a primary objective. So the idea is someone without a lot of detailed knowledge of physical design can bring RTL in, get a GDS out, and make a chip out of it. We're trying to lower the barrier to chip design and get more people to design chips. So on our website here, we have a lot of different resources. You can learn about the people who are in the project, various news and events, some publications, other outreaches that we have. You find a link to our GitHub project, a Getting Started guide, and some community discussion along with other resources. I encourage you to visit this website to learn more than the brief overview can give you today. So moving on to our GitHub project area, I want to show you that we have basically a top-level project area. And here there's a repo that basically has some brief introduction and where to start. More or less, this points you over here at the OpenRoad Flow repo, which is our top-level repo that integrates the different tools that we have. So the tools that we depend on are basically our top-level OpenRoad app, the detailed router, and Yosis for synthesis. So the top-level repo basically integrates all of this, has a makefile to run designs all the way from RTL to GDS, has the ability to build OpenRoad and all of the necessary components. So this is basically your place for one-stop shopping where you can download everything that you need and run a design. If you look through the introduction here and the README, it basically talks a little bit about what I've just talked to you about. You know, our goal is no human in the loop, 24-hour turnaround time. We go through the code organization, the different dependencies that we have, and then you have a couple of options on how you want to run. You can build, or you can use pre-built binaries. You can build locally using Docker if you don't want to install the build time dependencies, or you can build the tools locally, and that's kind of up to you. Certainly, if you're going to contribute code, you want to be able to build locally. So I also wanted to mention that there's a top-level app called OpenRoad, which is basically the heart of where all of the different engines are. And I'll talk a little bit more about this in detail. I do want to get the demo started because it takes about 10 minutes to run, and it can run in the background while we're continuing to talk about OpenRoad. So here you can see I have a Unix prompt open. On the left side, I'm basically sitting in the top level of the OpenRoad Flow repo. You can see the script that would build it, a Docker file, which if you're using Docker defines the dependencies. Then there's a Flow directory, which has the Flow scripts, and the tools directory, which I showed you, which basically has the tools inside it. So moving over to the Flow directory, You can see here that we have platforms, which is where you put your PDKs. We give you by default a NAND gate 45 PDK, and if you've created other ones for Open Road, you can put them in there. This demonstration will be focused on GF14. So you can see in our platforms directory that we have some private data for GF14, which will be used in the PDK. I also wanted to show you just at the top level, I'll be running the design AES. We have a bunch of prepackaged designs. Here I'll be running the AES design in GF14. So before the demo, I already synthesized the design, and basically starting here with initializing the floor plan, doing initial timing analysis, and then running through the steps that you're used to in an EDA flow: global placement, detailed placement, routing, optimization, timing analysis, and at the filler cell insertion, fill, and at the very end, streaming out a GDS. So I'll let this run in the background while we continue to look a little bit more at the Open Road Flow repos and some details about the technology. Okay, so I think the first thing I want to mention is that in Open Road, we're working hard to make it easy to integrate designs. So if you look here at a makefile, let's say you wanted to add a new design named GCD, all you would have to do is in designs under the supported platform that it works with, create a makefile. And in this makefile, you just have to specify the design name, the platform, where the Verilog files are, where the SDC is, and the die and core area. There's an optional clock period if you don't want to specify an SDC, where you can just tell us a clock period and we'll automatically constrain the entire design to that clock period. And that's it. Basically, then you would type make, your design would be synthesized all the way through routing and GDS out, and then you'd be ready to make a chip. We're also very focused in Open Road of building something that's going to last. And one of the things that you just have to do when you're going to build software that's going to last is have a good development methodology. So here you can see that we're using Jenkins continuous integration. So we won't accept any code changes that come in unless they pass all of these tests. We also do code inspection on pull requests and really make sure that the contributions are written in such a way that they can last for the long haul. We also have a top-level dashboard for the project. So here there's a summary. Here I'm just looking at our GF14 data. And basically with every build, we get red, yellow, green. So here we can see the synthesis count went up. We need to investigate that. Maybe that's something that was intentional that made the design better. If we decide that's the new baseline, then the red would turn to either green or a blank color. Going down, we gather a whole bunch of metrics through the flow. These metrics eventually can be put into a database and used for machine learning. And you'll see various papers coming out of Open Road members about that. And through every step in the flow, we basically gather various statistics. You can see here that in our latest software build, this is not released. We caught this as a problem before it's going to go out. We have a couple of DRC violations on this design, and that needs to get resolved before we can have our next release. So this is a way as a project manager that I can see at the top level how releases are progressing. So we're very serious about our development methodology and making good code. Another aspect to that is that if you were going to contribute source code to Open Road, you can see here all of the contributed code already, a global router, top level, we call it ice wall, basically creates the top level IO ring and other things that are needed at the top level of an SOC. We have OpenDB, which is a physical database, a static timing analyzer, and on down the line. If you were going to contribute, we would also insist that you give us tests. And so we won't take any code that doesn't have fast running small white box unit tests. And here you can see a bunch of them. And they're good examples if you're going to add some new code of how you could make tests. So here I wanted to show you our Jenkins interface, which you can get to at jenkins.theopenroadproject.org. Here you can see all the different runs that happened, see what the log files look like, if there's anything unexpected in there, especially if there's a failure. This is a good place to go to see the details of what might have happened that went wrong. Just went back to the demo and you can see that the router has started now. It's on its first of 10 optimization iterations, driving down the number of DRC violations. And then once it hits 0, it will optimize the routing further. So here I wanted to talk a little bit more too about the different resources that you have. We have a Twitter page, we have a community on Gitter, you can file GitHub issues. You can see here that we have 9 issues open, and we do try to respond to them reasonably quickly. So if you do have an issue with the software or a question, that's a good place to go. You can see here on the OpenRoad top-level app, we also have issues, and what we do is you can file issues to the top-level flow, or you can file them to each individual app as well. You see we have several branches. So in the documentation, you'll find a bunch of useful articles. One of the best one is the OpenRoad architecture document, where it talks about the tool philosophy, the tool file organization, which directories you have to create to add a tool. Goes through the various dependencies, how we do the builds, the workflow with Git, and how to deal with submodules in Git, which can be complicated. And then at the bottom, you'll find a pretty detailed tool checklist, which you can go through if you were going to contribute some code. We would want you to go through that checklist. So you can see here, we're at the 9th routing iteration. We're just going to finish up the routing here. It doesn't take too long. You can see it's already driven the DRC violations down to 0. Basically, it's just working hard now to improve the routing. Now that the routing is complete, it will do a little bit of post-processing and then stream out a GDS. Also doing timing analysis and various other reports that are interesting. And now we have a GDS. So you can use the K-Layout layout viewer, which is an open source layout viewer to view the GDS. So I'll bring that up here. And once it loads, I'll cut the display to just show the top. It's a lot more interesting to look at just the top level. And here you can see basically your SOC. You have your IO ring, you have the power and ground mesh, and you have all of the details that you would expect to see in a FinFET node VLSI layout. As we zoom in, you can see the details of the place and route, the filler cells, the fill, the detailed routing, the vias, etc. Well, thank you very much for your time and attention, and enjoy the rest of your virtual conference. Thank you.
Next, Mohammed Shalan will tell us about OpenLane.
Hello everyone, my name is Mohammed Shalan. I'm an associate professor at the American University in Cairo. Also, I'm a consultant for eFabrics Corporation. Today, I'm going to present an open source ASIC flow. We refer to this flow as OpenLane. We developed OpenLane for a true open source tape-out experiment. When we use the term open source integrated circuit, we usually refer to the fact that the design files are open source and they are downloadable. Anyone can download them and can replicate the design, independent of what tools are used to design. And usually commercial tools are used to carry out the design activities. Here we mean by open everything. Open SSL library, open physical design kit, open design files, OpenFlow, and OpenEDA tools. In today's talk, I'll be given an overview about OpenLane and its capabilities. Also, I'll be given an overview about Strive, the open source SoC that was taped out using the OpenLane flow. Finally, I'll be discussing some of the issues faced during the design, also the contributions done by the OpenLane team to the open source EDA ecosystem. OpenLane was developed for a true open source tape-out experiment. In this experiment, we wanted to have everything to be open source. And that includes, but not limited to, the design, the standard cell library, the EDA tools used for tape-out, the physical design kit, and to achieve so, we developed OpenLane to be an open source ASIC design flow. Our main goal for OpenLane is to have open everything push-button flow that can produce clean GDS2 starting with RTL. We have been working on it since last fall. We successfully built it and used it for almost open tape-out. I'm saying almost because eventually everything was open except of the standard cell library. Currently, we are working on the next tape-outs, but this time they will truly be open. OpenLane was built around open source EDA tools mainly from the OpenRoad and Qflow projects. Also, we developed some tools to address issues and fill in some gaps faced during the development. At the moment, the flow supports an OpenPDK for 130 nanometer commercial fabrication process. More details will be released soon. At the moment, I cannot reveal more than that. Also, it was ported and tested with closed PDKs from GlobalFoundry and XFAB. OpenLane was developed mainly to tape out Strive. Strive is a small SoC built around one of the RISC-V CPU cores, the Pico RV32. We add few peripherals to the SoC such as general purpose input-output, universal asynchronous receiver transmitter, serial peripheral interface master. Also developed small or digital PLL for clocking. For on-chip memory, we use 1 kilobyte of synthesized SRAM block. In the future tape-outs, we will replace this synthesized SRAM block by SRAM blocks generated by UC Santa Cruz OpenRAM tool. Strive doesn't have any analog peripheral, but this will change in future tape-outs. So in order to tape out Strive, OpenLane has to support the hardening of individual Strive building blocks or macros, as well as Strive SoC top-level assembly. Here we have an abstract view of the OpenLane flow, where block colors reflect the component source, whether it's OpenRoad tool, Qflow tool, an existing open source EDA tool, or a tool developed to address an issue or fill in some gap. The flow starts with the uses and ABC for RTL and logic synthesis. Macro floor planning is done using OpenRoad. Chip level floor planning is done using Qflow path frame generator. Placement and routing are done using OpenRoad. Clock tree synthesis and antenna diodes insertion are done using tools developed by the OpenLane team. Magic and NetGen are used for physical verifications. The flow lacks important components related to time enclosure and design for testability. These areas are being addressed at the moment and will be supported with the future releases of OpenLane. This table shows a small snapshot of designs we are using to test and benchmark OpenLane. Currently, we have around 50 benchmark designs. As you can see, we can tackle relatively large synthesized macros. The largest in our benchmark suite consists of almost 1 million logic instances. As the table shows, OpenLane is able to produce almost clean GDS2. Even though the numbers of violations reported by this table are small, we understand the root cause of these violations, and at the moment we are working on addressing them. So our latest updates to OpenLane are expected to eliminate these violations completely. And if not, we'll reduce them into few. These numbers were obtained using the OpenPDK with commercial standard cell library, as the integration of the open source standard cell library is still work in progress. The first Strive SoC was taped out more than a month ago. The layout was automatically generated by the OpenLane flow, starting from RTL source files. We only needed to touch the final layout for two things. First, to solve some LVS errors, and second, to connect the power distribution networks of the macros to the power paths. At the moment, we are working on taping out updated version of Strive. Strive 2 replaces the synthesized SRAM in Strive with SRAM generated by UC Santa Cruz OpenRAM. At the moment, the OpenRAM team is porting it to the OpenPDK. Strive 3 will be using Oklahoma State University Single Cell Library, which has been ported to the OpenPDK, but the OSU team is addressing some issues reported by us. The plan is to tip out Strive 2 and Strive 3 in 2 weeks from today. Beyond Strive 3, we are planning to add more digital peripherals. Also, we plan to introduce analog peripherals. And finally, we are going to change the design hierarchy and methodology in order to achieve a true push-button flow. We have been working closely with the OpenRoad team to address any emerging issues while constructing OpenLane and taping out Strive. For that, we have weekly meetings discussing the issues and the workarounds. We report issues and request features. The OpenRoad team is actively addressing them and helped us achieving a successful tape-out. For that, we filed more than 25 GitHub issues. In several occasions, we have to debug OpenRoad tools in order to understand the root cause of the errors issues we are facing, in order to implement workaround for them. Eventually, this has resulted in more than 10 GitHub pull requests to fix issues and add new features to existing OpenRoad tools. Here are some OpenLane issues. Currently, we are focusing on producing a clean GDS2 automatically. We have been ignoring time enclosure. This will change in near future. OpenRoad clock tree synthesis tool does not generate a valid clock tree using the OpenPDK. For that, we had to create our own clock tree construction tool. It's not as great as Triton CTS, but it's good enough for the tape out. OpenRoad routers are grid-based. Because of that, we had pin access issues with several cells from commercial and open source single cell libraries. Almost all single cell libraries are designed to be used with commercial routers, and commercial routers support gridless routing. This was not an issue for Strive tape-out using commercial single cell library with hundreds of cells. We only needed to exclude some cells that cause these issues. For Oklahoma State University single cell library, it was an issue given that the single cell library has only around 60 cells. OSU team is addressing this issue at the moment, and the OSU single cell library will be updated soon to be friendly to OpenRoad routers. Most of the layout issues we have were related to the Deter router, Triton route, causing short circuit errors, trying to solve DRC errors. We isolated the issue and we are working on a fix for that. Top level power routing has to be done manually at the moment. This being addressed in different ways to achieve 100% layout automation. Finally, to solve antenna errors, OpenLane is spraying the design with antenna diodes. This solves the problem, but introduces timing issues. It was okay for Strive, as timing wasn't a priority. Currently, we are working with OpenRoad team to address this during routing. Also, we independently working on the methodology to address the antenna rules violations. Going forward, we are working on enhancing OpenLane on many fronts. To make it a truly open everything flow, Oklahoma State University Single Cell Library is being integrated at the moment. Also, a better handling of the antenna rules violations is in the work as well. Finally, in near future, OpenLane will have support for both design for testability and time enclosure. I'll be happy to address your questions if you have any. Thank you.
Thank you again, and we look forward to your questions in the app and in Sunday's Q&A session. Have a great ISCA, everyone.